which groups will make the carbocation more stable and which will make it less stable. Similarly for carb anion, right? This is having this cyclopropane ring, and in this carbon, on this carbon, the carbocation is present. Less the double bond character, longer will be the bond, right? Hello students, welcome to Alan Overseas and welcome back to the very important series that we have started, is 45 important topics in 45 days, okay? And we have divided this series in 3 parts, that is 15 from physics, 15 topics from chemistry and 15 topics from mathematics, right? This is how we are going to cover the total 45 very important topics in 45 days, right? So, you know that I will be covering the chemistry part, and here is the next topic of chemistry, that is stability of intermediates, acidic and basic strength, that is taken from the chapter GOC, that is General Organic Chemistry. Fine. So now let's start this topic. First of all, we have to see the stability of reaction intermediates. Okay, reaction intermediates are those species which are formed during a reaction, right? That's why we are calling them as intermediates. So for example, we have carbocation, carb anion, free radical, etc. Right? So how to find out the stability order for these intermediates? So when we talk about the stability of carbocation, okay, carbocation, positive charge on the carbon. So which groups can make the carbocation more stable, or which kind of groups can make the carbocation less stable? So when carbocation is attached to an electron donating group, so electron donating groups increases the stability, of carbocation, increases the stability of carbocation, right? Because electron donating groups are donating electrons and making the carbocation electron rich kind of, okay, not electron rich but kind of, we can say completing its electron deficiency, fulfilling the electron deficiency, right? So they are making it more stable. On the other hand, when you have electron withdrawing group, electron withdrawing groups are withdrawing the electrons from the carbocation, that means making carbocation more electron deficient, okay? That means they will be decreasing the stability, decreases stability of carbocation, right? Decreases the stability of carbocation, right? And on the other hand, if we talk about the stability of carb anion means negative charge on carbon. So carb anions are electron rich already. So when they are having electron donating groups are increasing the electron density on carb anions, so making it less stable, because this carb anion is already electron rich, right? So when electron donating group is attached, that means they are decreasing the stability of carb anion. Whereas when they have electron withdrawing groups means they are withdrawing electron density from carbon anion, that means they are making it more stable. So in presence of electron withdrawing groups, stability increases, stability of carbon anion increases, right? So this is how we can find out that which groups will make the carbocation more stable and which will make it less stable. Similarly for carb anion, right? Now let's see. Okay, now what should be the priority order? We know we have few effects which are contributing in this stability of carbocation or carb anion. For example, we have inductive effect, hyperconjugation, mesomeric effect, back bonding, resonance, etc. So what should be the priority order of these effects? So first of all, the first priority is given to back bonding, then mesomeric effect, after that we have hyperconjugation and inductive effect. This priority order we have to follow while checking the stability of carbocation or carb anion. For example, if I'm talking about stability of carbocation, so it will be directly proportional to, first of all, the back bonding. If you have back bonding, that will be maximum stable. After that, you have mesomeric effect, and in mesomeric effect also, the plus M effect, which is electron donating effect, will make the carbocation more stable. After plus M, you have hyperconjugation effect, okay, and then inductive effect plus I effect, okay. This will be the priority order for the stability of carbocation. Similarly, when we are talking about stability of carb anion, so here also if you have any back bonding effect, then that will be more stable. Then instead of plus M, you have minus M. After minus M, if you in carb anion, we'll be discussing about the minus I effect, okay, electron withdrawing effects. So these orders, these priority orders we have to follow while checking the stability, right? Now let's see one question related to the stability of intermediates. So here we have to find out the order of stability for the following intermediates. So first of all, you have carbocations, okay. So here in the first part, we have CH3, CH2D and CD3 carbocation. D is deuterium, that is the isotope of hydrogen, right? So if I talk about the plus I effect order for hydrogen, deuterium and tritium, the three isotopes of hydrogen, then plus I of tritium is maximum, then deuterium, and then for hydrogen it is least, okay. This is the order for plus I effect for these three isotopes. That means if in a carbocation, in a compound, in a species, if tritium is present, that will be making the carbocation most stable as compared to deuterium and normal hydrogen, right? So as the number of deuterium increases, the stability of carbocation also increases because plus I effect is increasing. Similarly, in the second one, hydrogen, deuterium, tritium. So tritium is having maximum plus I effect, that's why increasing order, right? In the third one, here you can see this is the carbocation and you have NO2, NO2, NO2 group. The position is different, okay. Now you can see that NO2 group, in the first part, the NO2 group is farthest from the carbocation, okay, and here it is little nearer and here it is nearest to the carbocation. So what is the effect of nitro group on the stability of carbocation? So we know nitro group is highly electron withdrawing. It shows minus I effect. It is showing minus I effect. It will withdraw the electron density, okay, withdraw the electron density. But we know inductive effect is distance dependent. So as the distance increases, the effect of inductive effect decreases, okay. So the maximum minus I effect will be here in the third case. Maximum minus I effect means least stable carbocation. So this will be least stable. As compared to first and second also, in the second comparatively, nitro group is close to the carbocation, that means it is also less stable. So the first one will be most stable because the minus I effect is away from the carbocation, okay. So we are going to get the decreasing order, right? Now let's see the fourth one. In fourth one you have, okay, this ring, heterocyclic ring, here you have oxygen and this is the carbocation. The position of carbocation is different here, okay. So in the first case, the oxygen is also highly electronegative, so it will apply minus I effect. It is applying minus I effect, okay. In the second one also same, it is applying the minus I effect. And in the third one, now it is not applying the minus I effect. Here actually you can see the lone pair and the positive charge in conjugation. So here actually the lone pair of oxygen, it is showing back bonding with the positive charge. So this is the case of back bonding. This is the case of back bonding. So we can say that this carbocation is stabilized by back bonding. So the third carbocation will be maximum stable, okay. So this is maximum stable. Now as compared to first and second, in second the minus I effect will be more because the distance between oxygen and carbocation is less comparatively, and in the first one the distance is more, so minus I effect will be less. Okay, so if I give these compounds a name like this is A, let's say this is B and this is C. So what will be the order? C will be maximum stable. Now in A and B, A is more stable and then B. Okay, so C, A, B, this order we are getting, right? Now let's see the next. In the fifth one also you have the carbocations. Okay, so here you can see that you have this ring. This is benzene ring. Here you have a double bond. In the third one you have two double bonds, and in the fourth one you don't have any double bond. Okay, so here when this carbocation is present on the carbon attached to the benzene, this is called as benzylic carbocation. So first one is benzylic carbocation, that is most stable as compared to all the others. Why? Because of the resonance. Okay, this carbocation is involved in the resonance with the 3 pi bonds of the benzene ring. So benzylic carbocation will be maximum stable. So let's say this is A, this is B, this is C, and this is D. So we are saying that A is maximum stable. Okay, now as compared to B, C and D, in C you have two double bonds, so there will be more conjugation, or we can say extended conjugation. So that's why C will be more stable as compared to B and D. So after A you have C. Now in B and D, in D there is no conjugation, no resonance, but here in B you have the conjugation. So this carbocation is more stable. The B one is more stable as compared to D. So we are getting A, C, B, D order. Okay. Now similarly we can solve the next one. Here all are benzene rings. So how we can check? Okay, we know that this carbocation is involved in the resonance with the benzene ring, with the 3 pi bonds of benzene ring, and after conjugation in resonance we know this positive charge will come at the ortho positions and para position. So when this positive charge will be coming at the para position, these hydrogens, this is a methyl group. So this methyl group is having 3 hydrogens. So these 3 hydrogens, they will be showing hyperconjugation with the positive charge. So hyperconjugation means here we can say it is having 3 alpha hydrogen. So let's say this is A. Okay, the second one, this is B, this is C, and this is D. Okay, so first one is having 3 alpha hydrogen. In the second one, this is the alpha carbon. So here how many hydrogen we have? We have 2 hydrogen atoms. Okay, so we can say 2 alpha hydrogen. In the C, we have only 1 hydrogen at this carbon. This is alpha carbon. So we have only 1 alpha hydrogen. But in the D1, you don't have any alpha hydrogen because there are 3 methyl groups. Okay, so 0 alpha hydrogen, right? So now we know more the number of alpha hydrogen, more will be the hyperconjugation, more stability of carbocation, right? So that's why A will be most stable, then B, and then C, and then D. So A, B, C, D, this decreasing order we are getting here in this question. Okay, now the 7th one. In the 7th one you have cyclic compounds. Okay, this is cyclobutane carbocation, and this is, okay, this is having this cyclopropane ring, and in this carbon, on this carbon the carbocation is present. Okay, and this carbocation having this cyclopropane ring, this carbocation will be more stable here. Why? Because here dancing resonance will be present. Dancing resonance. In this cyclopropane ring, this dancing resonance will be present, and due to which this carbocation is more stable as compared to the first one. Okay, this dancing resonance, what happens? This sigma bond here breaks, okay, and shifts here and makes the double bond. So it will be converted to, this structure. Here the double bond, and this will be the positive charge. Similarly, another resonating structure, this will be like this. Okay, this resonance where the sigma bond is breaking and shifting and making these resonating structure, this is called as dancing resonance, and due to this dancing resonance, this carbocation becomes more stable, and actually it becomes more stable as compared to benzylic carbocation. So that's why this is very stable carbocation, right? So that's why second is more stable. Fine. Now let's see. We have seen the order of stability for the carbocations. Now let's see the acidic strength. Okay. So what is acidic strength? What is acidic nature? Let's see first of all. What are acids? So the species which can accept the lone pairs of electrons relatively easily, or which can produce stable anions after deprotonation, are said to be more acidic as compared to the others. Okay. So first of all, when we are comparing the acidic strength, either the species should have the tendency to accept the pair of electron easily, accept the lone pair of electron easily, or they can produce stable anions after deprotonation, after giving H plus ion. Okay. So in any situation, if it is happening easily, that means that compound will be having relatively more acidic strength. Okay. So acidic strength, on which factors it depends? First of all, stability of conjugate base. Conjugate base means, suppose I have this HA acid. So when this HA acid is donating H plus ion, so this anion will be formed. Okay, this anion will be formed, and this is acid. So this A negative will be called as conjugate base. Conjugate base of the acid, conjugate base of this acid, right? So stability of conjugate base, more the stability of this conjugate base, more will be the acidic strength, right? And electron withdrawing group on the conjugate base. Now which groups can make this conjugate base more stable? So electron withdrawing group, if electron withdrawing groups are attached to this conjugate base, they can make it more stable, right? And directly proportional to Ka value or pKb value, right? So based on the K and pKb value also we can find out the order of acidic strength. Fine. So now let's solve the question related to this. So this is the question. Compare the acidic strength of the following species. Okay. Here you can see you have these organic acids. So these two are the phenol derivatives, and this one, this is also having OH, but this is having carboxylic group. So carboxylic group is the principal functional group here, right? So how to compare it? First of all, if we talk about the strength of organic acids, so sulfonic acids are most acidic. Sulfonic acid, in organic acids, sulfonic acid will be most acidic. Then you have carboxylic acid, and least will be, comparatively, phenol will be less acidic. Okay. So we don't have sulfonic acid here, but we have carboxylic acid. So this carboxylic group is more acidic as compared to OH group, right? So if we talk about the first and second, here we are talking about the acidic nature of phenol. Acidic nature of phenol. So when they will be giving up the H plus ion, the carb anion, the conjugate base will be formed. And here you can see you have nitro group. Nitro group is minus M, the group which shows minus M and minus I effect, right? So this is the electron withdrawing group. Similarly, here cyanide also shows the same effect, minus M and minus I effect, right? Okay. Now this is the acidic group for the third compound. Okay, comparatively more acidic. So this carboxylic acid will donate the H plus ion, right? So for that conjugate base, this OH group is showing plus M effect. Okay, this OH group is showing plus M effect because oxygen is having lone pairs. Okay. Now doesn't matter this group is showing plus M effect or minus M effect or whatever effect, whatever group is present here. Comparatively, compared to phenol, carboxylic acid is always more acidic. So we can say that third will be most acidic. If this is A, this is B, this is C. Okay. So as compared to these two phenols, carboxylic acid is still more acidic. So C will be most acidic. Now in A and B, both groups are showing the same effects, but minus M effect of nitro group is more as compared to cyanide group, right? So more the electron withdrawing nature, more will be the acidic strength, right? So after C you have A and then B. So CAB, this will be the decreasing order for the acidic strength of these compounds, right? Now in the second example, you have, okay, all are phenols. You can see all are phenols now, phenol derivatives. This is the first one where one nitro group is present at the para position. In the second, nitro group is present at the ortho position. In the third, you have 2 nitro at ortho and para. And in the fourth one, you have 3 nitro groups. Okay. So we know nitro group is electron withdrawing group. Highly electron withdrawing group, all are showing minus M effect. At ortho and para, they show minus M effect. Okay, here also minus M effect and minus M effect. Okay, so in these 4 compounds, I can say the fourth one will be most acidic. So let's say this is A, this is B, this is C, and this is D. So I can say that D will be most acidic because it is having 3 nitro groups, right? So the conjugate base will be maximum stable here. Now after that you have C, because this is having 2 nitro groups. So this will be second, this will get the second position, right? Now between A and B, both are having 1 nitro group. So minus M effect does not depend on the distance, but minus I effect depends on the distance. So this is having minus I effect, this is also having minus I effect. So comparatively, the B should be more acidic. But there is one more condition here. In the B, intramolecular hydrogen bonding is present. Between this hydrogen and the oxygen of nitro, intramolecular hydrogen bonding will be present, okay, between the oxygen and this hydrogen, okay. So due to this intramolecular hydrogen bonding, when this hydrogen is involved, the hydrogen of the OH is involved in the intramolecular hydrogen bonding, this will make this molecule less acidic, okay, because now this hydrogen is not comparatively free to be donated, right? So that's why the B will be having least acidic strength comparatively compared to all the other compounds, okay. So now we can say that after C you will have A, and then B will be having minimum acidic strength due to intramolecular hydrogen bonding between hydrogen and oxygen of the nitro group, right? Fine. Now let's see. Now there is this particular effect that is called as steric inhibition of resonance, that is called as SIR effect. Okay. Due to this SIR effect, the acidic strength is kind of affected. How? Let's see. What is this SIR effect? Let's understand, then we'll see how it affects the acidic strength of benzoic acids. So let's see. Whenever bulky groups are present on the ortho position with respect to a triangular group, due to steric repulsions, the triangular group goes out of the plane, due to which extent of resonance of the triangular group with the ring decreases, and this is called as SIR effect. So this is saying that on the ring, when you have triangular group means the group which is having trigonal planar geometry, okay, that is called as triangular group. So if like nitro is triangular group, right? So when this triangular group is present on the ring and at the ortho position, this is the ortho position, at this ortho position if some group is present and this group is a bulky group, then what will happen? Between this triangular group and this ortho group, there will be steric repulsion, and due to this steric repulsion, the nitro group will go out of plane, okay. Suppose this is the plane of benzene, and initially the nitro and the benzene, they were in same plane, but due to this steric repulsion caused by the ortho group, now the nitro group changes the plane. It goes out of plane as with respect to benzene. And we know for the conjugation, for the resonance, the all the pi bonds, all the groups which are participating in the resonance, they should be in same plane. But when nitro goes out of the plane, then now resonance between the nitro and the benzene or whatever triangular group you have, the resonance between that triangular group and benzene, that resonance decreases, okay. That resonance is inhibited. So that's why this effect is called as steric inhibition of resonance, okay. So this is SIR effect. Now what are the consequences of this effect? So let's see. Due to steric repulsions from ortho position, NO2 rotates itself out of the plane of the ring. Due to this, resonance of NO2 with the ring is inhibited, and this phenomena is called as SIR effect. And due to SIR, the extent of resonance of nitro with the ring decreases, okay, and this resonance will be decreases. Now, due to this decrease in resonance, what will happen? Let's see. We'll understand with the example. So this is the question here. You can see you have these carboxylic acids. So basically, carboxylic acid is also a triangular group. So when at ortho position, when some groups are present, they will cause the steric repulsion, the SIR effect. Due to the SIR effect, the carboxylic acid group will go out of plane. Okay. For example, here in the Y, you have methyl here, CH3, and in the third one also you have two methyls. Okay. Both methyls will be showing the SIR effect. So this methyl is showing SIR effect. Here also the two methyls are showing SIR effect. Due to this SIR effect, we know the resonance of benzene with this carboxylic acid, this is inhibited, and due to this inhibition of resonance, what will happen now? If I make the conjugate base of this acid, then it will be like this. This is the carboxylate group, CH3 and CH3. Now, you can see that this conjugate base, this cannot participate in the resonance with the benzene ring, right? So, there will be resonance, but between these two oxygen only. So, due to this resonance only, now you will be getting two resonating structures, but those two resonating structures will be equivalent resonating structures, okay? So, equivalent resonating structures are more stable as compared to non-equivalent resonating structures, right? So, due to more stability of these equivalent resonating structure, this conjugate base will be most stable, okay? This will be more stable conjugate base. And in all these three compounds, this will be most stable conjugate base, because due to resonance in this carboxylate group only, you are getting equivalent resonating structure that makes the carbon ion more stable. So that's why more the stability of conjugate base, more will be the acidic strength of the corresponding acid. So that's why we can say that if I compare the acidic strength of these three compounds, this is A, this is B, and this is C. So if I write the order of acidic strength, for these three compounds, then we can say C will be most acidic, then B, and then A, okay? Here you don't have any SIR effect, right? But we have to compare the bond length in this question, X, Y, and Z. So we know bond length is directly proportional to partial double bond character. If any bond is having partial double bond character or double bond character, then it will be, the bond length will be decreasing. As the bond order increases, bond length decreases. So here we know this carboxylic group will be showing the resonance with the benzene ring, right? Due to resonance, there will be partial double bond character between the carbon of benzene and carbon of carboxylic acid. So we can say maximum pi bond character, maximum double bond character in the bond, maximum double bond character in X bond, okay, in X. Whereas comparatively the C1, where the resonance is least, okay, due to SIR effect by two ortho groups, the resonance will be least. Least resonance means here there will be least double bond character in Z, okay. So less the double bond character, longer will be the bond, right? So comparatively we can say if in X, Y, and Z, Z will be X, Y, and Z, Z bond length will be maximum and X will be minimum. This will be the order of bond length, right? Now let's see another question. This question you have to compare the acidic strength. So now again carboxylic acids, the benzoic acids are given, and here nitro group is present at para, meta and ortho. Okay, when nitro group is present at ortho position, that means it will be showing the SIR effect. SIR effect. And for carboxylic acid, this SIR effect is also called as ortho effect. This is also called as ortho effect. Now look, there is one point that you have to remember. When we are talking about this ortho effect or SIR effect, then the nature of this group doesn't matter here. Like it is showing positive mesomeric effect or negative mesomeric effect. That doesn't matter now, okay? If you have any bulky group present at the ortho position, it will show SIR effect, and due to SIR effect, the acidic strength of benzoic acid will increase. Okay, so in all these three, due to SIR, the third one will be having the maximum acidic strength. So suppose this is A, this is B, and this is C. So we can say C will be most acidic, right, due to SIR. Now in A and B, at para position, the nitro group shows -M and -I both effects, right? More the electron withdrawing nature, more will be the acidic strength. But at meta position, nitro group does not show, or any group at meta position, mesomeric effect does not work. So at meta, only -I effect will be working. Okay, so comparatively A will be more acidic. So after C you have A and B. B will be least acidic among all these acids. This is how we can compare the acidic strength applying the SIR effect also, right? Now we have to see the basic strength. Okay, so the species which can donate their lone pairs of electrons relatively easily, or which can produce stable cations after protonation, are said to be more basic as compared to the others. Okay, so what are bases? Bases are those species which can donate a pair of electron easily, or which can accept one H plus ion, means protonated, and after protonation they make more stable cations. Okay, so after accepting H plus ion, they will be making their conjugate acid. So here we have to compare the stability of conjugate acids. So that's why basic strength is directly proportional to stability of conjugate acid and electron donating group on conjugate acid. On which factors the stability of conjugate acid depends? It depends on the electron donating groups. If electron donating groups are attached around it, that means they will make conjugate acid more stable, and that's why basic strength will also increase. Okay, and directly proportional to Kb and directly proportional to pKa value, right? Now let's see one question related to this. We have to compare the basic strength of these compounds. So let's see. In this first one, you have this A and B. We have to compare their basic strength. So the first one, the A1, this A is called as pyridine. Here on nitrogen, you have a lone pair. Okay, this is A. This is called as pyridine. Okay, and the second one, here also on nitrogen, you have a lone pair. This is called as pyrrole ring. Okay, in pyridine, the lone pair on the nitrogen is not participating in the resonance, in the conjugation. Okay, so this is a localized lone pair. This lone pair is localized. This is localized. Okay, it is not participating in the resonance. Whereas this lone pair is delocalized, it is participating in the resonance. And one more thing, due to this resonance, this ring, this 5-membered ring is becoming aromatic. Due to these lone pairs, this compound is aromatic. So if this compound donates this electron pair, then the ring will become non-aromatic. Okay, and that will make it less stable. That will make the conjugate acid less stable. So that's why this B compound cannot donate the lone pair. Okay, so the the basic strength of the second compound will be less as compared to A. In pyridine, the lone pair is free, so this nitrogen can easily donate the pair of electron because it is not participating in the resonance, right? It is localized. So we can say that A is more basic as compared to B. So whenever due to the lone pair If the compound is becoming aromatic, then in that case that compound will be least basic, because if the compound donates that lone pair, the compound will become non-aromatic and that will become less stable, right? Now let's see the next. In the next example, let's say this is A, this is B and this is C. Okay, so here you have oxygen in the first one, oxygen having two lone pairs, and on this nitrogen, what will be the effect of oxygen? Oxygen will be withdrawing the electron density from the nitrogen, because the electronegativity of oxygen is more as compared to nitrogen. So basically here it is applying minus I effect. Minus I effect, okay. In the second one you have nitrogen, and here you don't have any electron withdrawing group. So these carbon chains, they are providing plus I effect, okay. So increasing the basic nature of this nitrogen. And in the third one, here also you don't have any electron withdrawing group. So plus I effect will be working due to these carbon chains, and methyl is also showing the plus I effect. So from three sides the nitrogen is gaining or getting plus I effect. So that's why overall the basic strength of this nitrogen, this compound will be maximum. Plus I effect increases the basic strength, right? So I can say that C will be most basic, and then B, and A will be least basic due to minus I effect. Okay, this is how we can compare the basic strength. Okay, now for the basic strength also we have a very important effect that is called as SIP, steric inhibition of protonation. That is basically applicable for the anilines. So this is aniline, you can see. So aniline, normal aniline, and this aniline where at ortho position you have a group, bulky group like methyl. Methyl is a bulky group. So what happens in this SIP effect? Let's see. If ortho position is occupied by a bulky group, steric repulsions increase after protonation. After protonation, the steric repulsions will increase, due to which protonation of ortho substituted aniline is inhibited, and this effect is called as SIP. Okay. Now if I talk about this molecule, so suppose this aniline, ortho substituted aniline, it accepts the H plus ion, means the nitrogen donates the electron pair to the H plus ion. So if it is donating electron pair to H plus ion, it will make conjugate acid. Okay, so this will be NH3 positive, and here you have methyl, that is also tetrahedral. Okay, so you can see now there will be steric repulsion between this methyl and this protonated group. Okay, and due to these steric repulsions, this structure, this conjugate acid is now less stable. So that's why this forward reaction will not be preferred. So we can say due to this group, due to this ortho group, the protonation of NH2 is inhibited. Okay, that's why we are calling it as steric inhibition of protonation. Due to the steric repulsion caused by the group present at the ortho position, the protonation of NH2 is inhibited. That's why it is called as steric inhibition of protonation. And here the basic strength will decrease. Due to this repulsion, due to this SIP effect, NH2 will not donate the pair of electron to H plus ion. That means now it is not able to act as a base. So that's why basic strength decreases here. Okay. In acids, in case of benzoic acid, the acidic strength was increasing due to SIR effect. But here due to SIP effect, the basic strength decreases. Okay. So let's see the question related to this effect now. Okay. Here you have these two questions. So suppose this is A, this is B, this is C, and this is D. We have to compare the basic strength. So you can see all are aniline derivatives. So in the first one you have methyl here at ortho position. That means SIP effect is working. Due to SIP effect, we know the basic strength become least. And in the other one, you have methyl group at the meta position, and here you have methyl group at the para position. So at para position, we know that hyperconjugation effect is also working. So here you have plus H effect, and plus I effect. Okay, so that's why this D, due to hyperconjugation, this D will become most basic, this D compound will become most basic, okay, comparatively. In the C1 here, methyl is present at the meta, so hyperconjugation will not work, only plus I effect will be working, only plus I effect, okay. Whereas in B, there is no such group, there is no electron donating group, right? So comparatively, I can say D is most basic. After D, you have C. After C, you will have B, okay. And A will be least basic due to SIP effect caused by the methyl present at ortho position. This is how we can compare. Now in the next one, here you have nitro group, but nitro group again present at the ortho position. So SIP effect will be working. Due to SIP effect, this will become least basic comparatively, okay. Now here you don't have any such group. In the third one, let's say this is A, again this is B, this is C, and this is D. So in the C compound, you have nitro group which is present at meta. So at meta, mesomeric effect does not work, so only minus I will be working. But at para position, minus I as well as minus M, both effects will be working, and electron withdrawing effects decreases the basic strength. So we can say that D will be, okay, D will be less basic, but due to the SIP effect, this A will become less basic even as compared to the D. So A will be, the A compound will be least basic. A will be least basic. After A, you will have D. Okay, after A, you will have D. And in B and C, B is not having any electron withdrawing group. So that's why comparatively B is more basic. So C and then B. B will be having most basic nature among all these compounds. Okay, so this is how you can compare the basic strength applying the SIP effect. Okay, so now that's it from my side on this topic. So we'll continuing this series. So don't forget to watch the complete series. The link for the playlist is given in the description. So stay tuned with us. Take care. Thank you.